In 2029 to Earth, something even from the orbits of our satellites, which are the guardians of our world, closer will pass. Could this be a real threat for us? And this, everyone's talking about interstellar comet not is, while 3 Atlas, with its exotic origin and harmless 268 million kilometer close pass headlines is adorning, a giant asteroid named Apophis, the biggest cosmic deception, is exhibiting, silently into the records passing in human history. The closest planetary close pass for is preparing. This will be the closest pass our species has seen. So is everything only this much? Of course not. In 2029, this mountain of rock and metal, 340 meters wide, from the moon 10 times closer will pass, moving with 7.4 kilometer speed. So much that wherever in the world you may be, this mountain of metal to the sky, when you turn your head, at that moment you will be able to see. But strangely, the tourist as a threat we see, the real neighbor coming to our door, however we ignore. As we will see tonight, the real question not is why to 3 Atlas we are stuck. The real question, why about Apophis we are not talking, is, if you are ready, we are starting. The real story of 3I Atlas, media deception, the truth behind the interstellar visitor. In the autumn of 2025, an event swept the astronomical media world. The interstellar object known as 3I Atlas, only with the title of the third confirmed interstellar visitor, created excitement all around the world. Humanity, for the third time with a traveler surprisingly coming to its galaxy, was encountering. Catalogued with the technical name C2025N1 Atlas, this alien comet appeared in the media with headlines such as "Alien Visitor Coming from Another Star System." But really, was it worth getting this excited? The story of the interstellar Comet 3I Atlas is actually a perfect example of how modern media distorts scientific facts. This cosmic visitor on October 30, 2025 will reach its closest point to the Sun, and then on December 19th will pass about 268 million kilometers away from Earth. This number may seem small to you, but actually, to picture this distance in our minds, the following example is quite enough. 268 million kilometers is exactly 700 times the distance from our Earth to our Moon, the panic atmosphere, created by the media. While our most advanced observation instruments like the James Webb Space Telescope and Hubble were closely following this interstellar object, media outlets were practically writing a horror movie script. Headlines like "Threat Coming from Space," "Mysterious Alien Comet Approaching" went viral on social media, while scientists calmly tried to explain the facts, because haste makes waste, and any wrong statement could cause a national chaos. The hyperbolic orbit of 3I Atlas means that it definitely will come once to our solar system and go away forever. This comet poses absolutely zero danger for Earth. No mathematical model, no law of physics, no orbital calculation can change this situation. The calculations are quite clear, and there is no need for more rumors. Have you ever thought, why do media outlets make so much noise about a harmless interstellar comet while staying silent about asteroids that could actually be dangerous? The point where things are just heating up starts exactly here. Scientific facts versus media. Scenarios. The scientific value of 3I Atlas is indisputable. This alien comet helps us understand the composition of materials coming from another star system. The spectroscopic data of the James Webb Space Telescope is extracting the chemical fingerprints of this cosmic visitor, while ground-based observatories are following the changes in its tail structure minute by minute. But the truly shocking thing is this. About this interstellar object that carries so much scientific importance, 90% of the news appearing in the media contains wrong or misleading information. So what is the right source for us? Whom should we trust? The orbital calculations of Comet 3I Atlas were checked dozens of times by NASA's Planetary Defense Coordination Office. The result is the same every time: zero danger. Experts of the European Space Agency also reached the same conclusion. This mathematical certainty is based on the orbital mechanics rules we have known since Newton's time. The real threat being overlooked. Things were starting to improve when right at that moment another truth appeared. So much had been focused on 3I Atlas that there was a truth everyone was overlooking. While 3I Atlas was drawing all the attention, Earth-near asteroids, NEAs, that really pass close to us and pose potential danger were being ignored. Every day on average 2-3 small asteroids pass from closer than the distance of the Moon. Most of them are harmless, but sometimes we can encounter surprises like the Chelyabinsk meteor. This meteor that exploded in Russia in 2013 was only 20 meters in diameter and injured more than 1,500 people. Interstellar objects like 3I Atlas, however, never make such surprises because they are one-time visitors. They come, they pass, and never return again. Technological developments and observation capacity. The discovery of C2025N1 Atlas is also a sign of how much modern astronomy has developed. Survey programs like Linear, Atlas, Neowise can detect such objects early by systematically scanning the sky. The infrared capacity of the James Webb Space Telescope is providing unique data about the composition of this alien comet. But the same technological infrastructure is also being used for the detection of potentially dangerous asteroids. For us, the paradox begins exactly at this point. Future missions like NEO-Surveyor will focus on the really important targets: dark, hard-to-detect asteroids that pose real threat. If it were you, to which research would you allocate more resources? To an interstellar comet that will pass once and go away, or to asteroids that regularly pass close to us and one day may cause trouble? Whatever you choose, right now the science world is completely focused on 3I Atlas, and this is quite worrying. What do you think about their choice affecting us? Public perception and science communication. The 3I Atlas case reveals the fundamental problem in science communication. Exotic and rare always attracts more attention, but this attention does not match real priorities. Interstellar objects are extremely valuable scientifically, but in terms of human safety, they are completely irrelevant. The media's alien visitor narrative distorts the public's perception of space hazards. While people remain unaware of real threats, they feel unnecessary worry about harmless objects. This is such an absurd situation. As if they are hypnotized, NASA's planetary defense coordinators are aware of this situation, and in every statement about 3I Atlas, they put the safety message at the forefront. But the media's sensational approach overshadows these messages. Lessons for the future. The story of Comet 3I Atlas gives us important lessons. How scientific discoveries are presented in the media directly affects public perception, and therefore science policies. While alien comet headlines get clicks, ordinary asteroid survey news is ignored. Future instruments like the Vera Rubin Observatory are not targeting objects like 3I Atlas, but NEAs that pose real threats. This is the correct approach, but for public support, it needs to be explained better in the media. And right at that moment, we realize this. The real problem is not the interstellar objects themselves, but our wrong perspective toward them. Looking from the wrong perspective makes it impossible for us to see the truth. What we must urgently do is to be able to look from the right perspective. 3I Atlas is a nice scientific opportunity, but completely irrelevant in terms of planetary defense. Are you also aware of this situation? Do the space news you see in the media really tell the things that matter, or only the ones that look attention-grabbing? The answer to this question will determine the future of planetary defense policies. The surprising transformation of Apophis from doomsday threat to scientific opportunity. The frightening discovery of 2004. On the night of June 19, 2004, Roy Tucker, David Tholen, and Fabio Bernardi, who were conducting a routine asteroid search at Kitt Peak National Observatory in Arizona, were about to make one of the most dramatic discoveries in the history of science. After this, the scientific world would never look at the universe the same again, and the architects of this discovery did not know this at the time. They detected a faint moving point of light in the sky and gave it the provisional code 2004. MN4, this asteroid, which looked ordinary, would soon receive the name 999942 Apophis and become the most closely tracked cosmic object by humanity. The first orbital calculations of Apophis gave a result that made astronomers' hair stand on end. This asteroid was calculated to have a 2.7% chance of impacting Earth on April 13, 2029, which was also Friday the 13th. Doesn't that ratio sound so small to the ear? Wrong. We must not forget that this was an astronomical probability. This ratio was the highest impact probability calculated up to that day and led to Apophis being assigned level 4 on the Torino scale, a record evaluation for a real object. This near-Earth asteroid, 340 meters in diameter, if it were really to impact, would release energy equivalent to 500 megatons of TNT and could completely destroy a large metropolitan area. This is a city-killer class asteroid, not creating global destruction, but large enough to take millions of lives. From uncertainty to certainty, the victory of science. But the truly shocking thing was that this 2.7% probability actually reflected scientific uncertainty, not a definite doomsday prediction, and the media could never understand this critical difference. The first observations were based on only 74 measurements over 64 days. This was extremely insufficient to predict the future position of an object with an orbital history of millions of years. At the moment the asteroid was discovered, there was no formal planetary defense infrastructure. NASA had various NEA detection programs, but there was no coordinated office for impact hazard assessment. The Apophis crisis radically changed this situation. Observatories worldwide mobilized. The Arecibo Radio Telescope, Goldstone Deep Space, Communications Complex, the European Space Agency's Space Situational Awareness Program, all began tracking Apophis. Have you ever thought, how could an asteroid organize the entire world so quickly? This was one of the rare, perhaps the only for moments when the world united the fastest ever. Must there always be a space threat to be able to unite and write? At that moment, the discovery by Don Yeomans and his team changed everything. By finding traces of this asteroid in archival photos taken before its discovery, they extended the observation time window back to March 2004. This dramatically reduced orbital uncertainties. 2029. Doomsday. Missed, science gained. Things were starting to improve when, during the 2005 apparition, the new data finally revealed the truth. Everyone was holding their breath waiting for the announcement. Apophis would not impact in 2029. However, the distance it would pass created the closest asteroid encounter in the history of science. Only 31,600 kilometers. How close is this distance? Our geostationary satellites orbit at 35,186 kilometers altitude. Apophis will literally pass between Earth and our satellite network. It will move like a tightrope walker. Apophis, in the category of potentially hazardous asteroid, has now turned from threat into scientific opportunity. In 2021, the detection of the Yarkovsky effect, a small thrust force created when the Asteroid absorbs sunlight and re-emits it as heat, eliminated all impact risks even for the year 2036. NASA's analysis confirms that Earth is safe from Apophis for 100+ years. April 13, 2029, humanity's cosmic appointment. If it were you, how would you feel when a 340-meter rock passes this close? Your view of space will probably be affected by this. So, will you be afraid? Or will this mystery pull you in even more? Apophis's 2029 flyby will be the first major asteroid encounter visible to the naked eye. Observers in Europe, Africa, and Western Asia will see a moving star in the sky. This closeness will allow us to observe the tidal forces created by Earth's gravity on the asteroid. The asteroid's rotation period, currently 30.6 hours, surface structure, and even its shape may change. These changes will allow groundbreaking observations in asteroid science. The OSIRIS-APEX mission, the renamed version of OSIRIS-REx, which brought samples from Bennu, will reach Apophis in 2029 and will study these post-encounter effects in detail for 18 months. This will be the first detailed analysis of the behavior of a near-Earth asteroid after such a strong gravitational perturbation. Planetary defense lessons taken from Apophis. The story of asteroid Apophis is the founding story of modern planetary defense. After this experience, NASA's Planetary Defense Coordination Office was established. The International Asteroid Warning Network was created. The Space Mission Planning Advisory Group became active. The DART mission was developed and successfully applied. The DART mission succeeded in changing the orbit of the asteroid Dimorphos by kinetic impact in 2022. ESA's HERA mission will examine the impact effects in detail in 2026. These successes are technological developments born from the Apophis experience. The cataloging of potentially hazardous asteroids continues rapidly. Survey programs such as Linear, Atlas, and ZTF discover thousands of NEAs every year. The NEO Surveyor mission will be launched in 2027 and will bring the capacity to detect dark asteroids. Risk communication, media, and science. And right at that moment we realize this. The Apophis case also revealed the fundamental problems in risk communication. But nothing has yet been done to solve this problem. That means right now we really have a big problem, and it is being ignored. The first 2.7% probability was presented in the media as certain doomsday. Yet this was only a temporary calculation based on limited data. Scientists now, with the lessons drawn from the Apophis experience, have developed better communication protocols for future asteroid discoveries. Early calculations are now presented with explicit uncertainty warnings, and the public is better informed about how the scientific process works. Asteroid 99942 Apophis carries the name of the chaos god in Egyptian mythology. Ironically, instead of creating chaos, this object caused the birth of modern planetary defense. This story, transformed from threat to opportunity, is the perfect example of how science deals with uncertainty and reaches certainty over time. Looking ahead, the post-Apophis era. Are you also curious what will happen when another asteroid like Apophis is discovered? You never thought about it, but we are more prepared for this than you imagine. Statistically, such a discovery is inevitable, but now we have the tools, protocols, and international cooperation mechanisms developed with the Apophis experience. When the Vera Rubin Observatory becomes operational in 2025, NEA discovery rates will multiply. This telescope has the capacity to discover more asteroids than all past surveys combined. Each new discovery will go through the analysis processes developed for Apophis. A more complete cataloguing of the near-Earth asteroid population will improve. Statistical risk assessments. Only 40% of potentially hazardous asteroids of 140 meters and above have been discovered. The rest are the target of future surveys. Apophis's 2029 encounter will be a final dress rehearsal for planetary defense. International coordination, real-time data sharing, rapid risk assessment, all protocols will be tested. This experience will form the rehearsal of how to act in the case of a real threat. Thus, we will know better what we can do against any threat that may come from space. Asteroid Apophis thus became the hero of the most dramatic threat to safety transformation in human history. From doomsday messenger to scientific opportunity, from panic to coordination, from uncertainty to certainty. This transformation is a unique story showing the power of the scientific method and international cooperation. Apophis, an ordinary but important neighbor, from discovery to disaster. One night changed everything. June 19, 2004 began like an ordinary night at Kitt Peak National Observatory in Arizona. Roy Tucker, David Tholen, and Fabrizio Bernardi, while continuing their routine near-Earth asteroid surveys, detected a faint point of light coming from the depths of darkness. At that moment, no one could know that this ordinary-looking rock piece would turn into the most closely observed asteroid in human history. No one imagined this, but it would be remembered as the greatest space danger approaching humanity. This object, coded as 2004 MN4, would soon take the name 99942 Apophis and carry the name of the chaos god of ancient Egypt. Why was this name chosen? Because it was foreseen that it would bring chaos. Apophis was not an exotic interstellar object, like 3I Atlas discovered by the James Webb Space Telescope. This ordinary rock and metal piece was the child of our own solar system. The first orbital calculations revealed an alarming truth. Apophis appeared to be on a collision course with Earth on April 13, 2029. This was not just a theoretical danger. The mathematical probability reached 2.7%. This number may sound small, but in terms of asteroid impact probabilities, it was astronomical. Is this number enough to keep you awake at night? Or does it sound insignificant? Record on the Torino scale the meaning of level 4. Apophis became the first real asteroid to receive a level 4 score on the Torino scale. This scale extends from 0 to 10, and most objects receive a score of 0, meaning they carry no collision danger. Level 4 is in the category of a close encounter that deserves the attention of astronomers. But here is exactly where things get complicated, because there had never been any asteroid that passed level 4 before. Apophis was the first asteroid that crossed this threshold. Unlike 3I Atlas, the threat of Apophis was real because it was following an Earth-crossing orbit. The interstellar comet 3I Atlas would come with a hyperbolic trajectory and disappear forever. But Apophis was different. With an elliptical orbit, it was constantly returning, each time carrying the potential to come a little closer to Earth. Observatories worldwide sprang into action. The European Space Agency's Space Situational Awareness Program, NASA's Near-Earth Object Program, astronomers from all over the world began to track Apophis. The whole world had become one heart against the approaching threat. From uncertainty to certainty, the victory of science. The story of Apophis, in fact, gives important lessons about uncertainty and risk communication. That first 2.7% probability was not a definite prediction, but a measurement of uncertainty based on limited data. Every new observation narrowed the orbit parameters of the asteroid further. As things started to go well, we noticed there was a problem. Don Yeomans and his team at JPL made a groundbreaking discovery. By finding archival images taken before the discovery of Apophis, they extended the observation span back to March 2004. These additional data dramatically reduced the orbit uncertainties. By the year 2005, refined calculations had reduced the 2029 impact probability to 0. Apophis really would make the closest flyby in history from only 32,000 kilometers, but it would miss. Learning this relieved us a little, but this story was only just beginning. Gravitational keyholes, future danger, the elimination of the 2029 threat did not end all concerns about Apophis. The concept of gravitational keyholes came into play. These narrow space regions, only a few hundred meters wide, if Apophis passed through them during the 2029 close flyby, could establish a certain collision in 2036. Unlike alien comets like C2025 N1 Atlas, the orbit evolution of Apophis could be closely tracked. The Yarkovsky effect, the fine rocket-like force created due to thermal emission asymmetry, could slowly change the orbit of the asteroid. Can you imagine how critical such fine calculations are? Scientists are trying to protect our planet from possible threats with such delicate calculations. The final solution in 2021, the measurement of the Yarkovsky effect. The final threat assessment of Apophis came in 2021. Independent teams succeeded in measuring the Yarkovsky effect on the asteroid with certainty. A drift of 70 meters per year in the semi-major axis was detected. This seemingly small change definitively excluded the passage through the 2036 keyhole and reduced the impact risk to 0 for at least 100 years. NASA's statement was clear. NASA analysis confirms Earth is safe from asteroid Apophis for 100+ years. This was one of the most comprehensive negative predictions in the history of planetary science. And this object, which once seemed certainly a threat, now began to be seen as a harmless one, near-Earth asteroids versus interstellar visitors. The story of Apophis reveals the critical differences between NEAs and interstellar objects like 3I Atlas. Interstellar comets make spectacular but harmless flybys, while NEAs create continuous and evolving threats. But if you think this is the only threat in our sky, you are mistaken. Have you ever thought about what the universe is expanding toward? I will talk about this in the next video, and also what kinds of dangers it may create for us. Apophis, in the category of potentially hazardous asteroids, PHA, meets the minimum orbital intersection distance criterion, a passage closer than 0.05 AU to Earth and a size greater than 140 meters in diameter. This threshold is not arbitrary. It represents the size that can create regional devastation. When the Chelyabinsk meteor struck the Earth, 1,500 people were injured. But the Chelyabinsk meteor was only 20 meters in size, whereas Apophis is exactly 7 times larger. Can you imagine the damage it would cause if it struck our world? 29. Transformation from threat to opportunity. April 13, 2029 will be a new beginning for Apophis. This encounter, which will occur on Friday the 13th, will be remembered not for superstition but for science. Passing inside the orbit of geostationary satellites, the asteroid will be visible to the naked eye. Tidal forces will test the structure of Apophis. Earth's gravity will be 50 times stronger than the asteroid's self-gravity and will probably trigger surface changes. Radar observations will document the changes with meter-level precision. Can you understand how unique this natural experimental opportunity is? We may never encounter such a thing again. OSIRIS APEX, the post-flyby scientific mission. The transformation of OSIRIS-REx into OSIRIS-APEX is a perfect example of mission repurposing. The spacecraft, which returned samples from Bennu, will reach Apophis in June 2029 and will conduct post-encounter analysis for 18 months. The thruster disturbance experiment will try to expose surface material and collect information about subsurface composition. This data will be crucial for future deflection missions. At that exact moment, we will make the discovery that will change the rules of the game. This systematic approach, unlike the episodic attention of exotic visitors like 3i Atlas, is establishing a sustainable planetary defense infrastructure. Apophis is the perfect example of an ordinary neighbor that transformed into a scientific opportunity and shows how we need to prepare against real threats. Section 4, Risk Assessment, Uncertainty versus Danger. Here's where the story gets fascinating and where most people completely misunderstand how space threats actually work. When Apophis first appeared on our radar screens in 2004, it didn't announce itself with flashing warning lights or dramatic Hollywood-style alerts. Instead, it whispered its potential threat through the cold, mathematical language of orbital mechanics and statistical probability. But here's the shocking truth. That initial 2.7% collision probability wasn't a prediction of doom. It was a confession of ignorance. Think about it this way. Imagine you're trying to predict where a baseball will land after watching it for only the first millisecond of its flight. You might have perfect physics equations, but your prediction could still be wildly wrong because you simply don't have enough data points. The same principle applies to asteroids, except the throw happened millions of years ago, and the landing might occur decades in the future. Every single observation of an asteroid, each measurement of its position against the background, stars at a specific time, helps scientists constrain the object's orbital parameters. But early in what astronomers call the observational arc, when you have only a handful of measurements spanning weeks or months, the uncertainties remain enormous. Small errors in individual observations can translate into massive uncertainties about future positions. The 3i Atlas comet, by contrast, presents no such uncertainty challenges. This interstellar object follows a hyperbolic trajectory that takes it nowhere near Earth's orbital neighborhood. Its closest approach of 268 million kilometers leaves absolutely no room for statistical ambiguity. When the James Webb Space Telescope and other observatories track this alien comet, they're studying a beautiful cosmic tourist that poses zero collision risk, not because we've calculated it to be safe, but because the geometry of its path makes collision mathematically impossible. This fundamental difference between uncertainty and impossibility shapes everything about how we should perceive space threats. Yet somehow, the media narrative consistently gets this backwards, treating the impossible as mysterious and the uncertain as resolved. The mathematics of fear. Let's dive deeper into what that 2.7% actually meant when scientists first calculated Apophis's impact probability. This wasn't some wild guess or sensationalized media fabrication. It represented the best estimate available given limited observational data. But here's what the headlines missed. That percentage was measuring our ignorance, not the asteroid's intentions. The concept of orbital uncertainty might sound like technical jargon, but it's actually quite intuitive. Every asteroid observation comes with measurement errors, tiny imprecisions in determining exactly where the object was at a specific moment. When you have only 74 observations spanning 64 days, as was initially the case with Apophis, those small errors compound into enormous uncertainties about future positions. Picture this scenario. You're standing at one end of a football field, trying to predict where a marble will roll based on watching its first few centimeters of movement. Even if you know the physics perfectly, tiny variations in your initial measurements could mean the difference between the marble stopping at the 50-yard line or rolling into the end zone. Scale that up to cosmic distances and decades of time, and you begin to understand why early asteroid predictions can be so unreliable. The interstellar comet 3i Atlas suffers from no such ambiguity. Its hyperbolic orbit means it's essentially in free fall past our solar system, following a trajectory that astronomical observations can pin down with extraordinary precision. When NASA and ESA scientists state that this alien comet poses no threat, they're not managing uncertainties, they're stating geometric facts. The keyholes that terrified scientists, but the Apophis story gets even more complex and more terrifying when you understand gravitational keyholes. During the asteroid's 2029 close approach, Earth's gravity will deflect its trajectory by a small but measurable amount. If Apophis passes through certain narrow regions of space during this encounter, regions only a few hundred meters wide, the gravitational deflection could set up a precision collision with Earth 7 years later in 2036. These keyholes represent a phenomenon unique to asteroid risk assessment that doesn't apply to interstellar objects. A close but safe approach can evolve into an eventual collision if the geometry aligns in precisely the wrong way. The keyhole for Apophis's potential 2036 impact was calculated to be roughly 610 meters wide, smaller than many city blocks, but large enough that early orbital uncertainties couldn't definitively rule out passage through it. And right here's where your understanding of space threats needs a complete reset. The 3I Atlas comet will never face such keyhole scenarios because its hyperbolic trajectory means it's leaving our solar system forever. One close pass, no return visits, zero cumulative risk. But near-Earth asteroids like Apophis are repeat. Customers coming back again and again, accumulating multiple opportunities for those rare but catastrophic geometric alignments. This is where the mathematics become both fascinating and frightening. Each individual close approach might have a very low impact probability, perhaps 1 in 1,000 or 1 in 10,000. But when an asteroid makes dozens of close approaches over centuries and millennia, those tiny probabilities begin to add up. It's like buying lottery tickets. Each individual ticket probably won't win, but buy enough tickets over time, and eventually, the psychology of probability. Here's where human psychology crashes headlong into astronomical reality. Our brains aren't wired to handle long-term statistical risks. We focus on immediate, dramatic threats while ignoring gradual accumulations of danger. A 2.7% impact probability sounds scary in headlines, but we instinctively treat it as either probably safe or definitely dangerous rather than what it actually represents, a measurement of how much we don't know. The 3I Atlas phenomenon perfectly illustrates this psychological bias. The interstellar object captures our imagination precisely because it's exotic and unprecedented. Alien visitor from another star. System writes its own headlines, complete with speculation about mysterious compositions and distant origins. Our pattern-seeking brains find the unusual inherently more compelling than the routine, even when routine events pose infinitely greater risks. Meanwhile, Apophis follows a perfectly ordinary near-Earth asteroid orbit. It's composed of common silicate rock and nickel-iron metal, materials found throughout the inner solar system. Its discovery required no revolutionary observational techniques, just the patient, systematic sky surveys that detect thousands of similar objects every year. By every measure except the one that actually matters, proximity to Earth, Apophis is utterly unremarkable. Yet Apophis briefly held the record for highest calculated impact probability of any known asteroid. Its early threat assessment reached level 4 on the Torino scale, unprecedented for a real object with a specific predicted impact date. That initial crisis mobilized observatories worldwide and forced the development of new protocols for asteroid risk communication that we still use today. The institutional response that changed everything. The astronomical community's response to the Apophis scare revealed just how seriously space agencies take near-Earth asteroid threats when they appear credible. NASA's Planetary Defense Coordination Office didn't exist when Apophis was discovered, But the crisis it generated helped justify the office's creation. The European Space Agency expanded its space situational awareness program partly in response to lessons learned from the Apophis experience. No comparable institutional response has emerged around 3I Atlas, nor should it. The interstellar comet poses no threat, requires no special monitoring beyond normal scientific observation, and offers no lessons applicable to planetary defense scenarios. It's fascinating but irrelevant to the practical work of protecting Earth from cosmic impacts. This institutional asymmetry reveals something profound about how we should allocate our attention and resources. Every dollar spent studying harmless interstellar visitors is a dollar not available for the unglamorous but essential work of near-Earth asteroid surveys. Every hour of telescope time devoted to exotic comets is an hour not spent tracking potentially hazardous asteroids that might pose future threats. The resolution that proved the system works. The happy ending to the Apophis story demonstrates exactly how planetary defense should work when confronted with apparent threats. As additional observations accumulated between 2004 and 2006, that terrifying 2.7% impact probability gradually shrunk towards zero. More data points meant smaller uncertainty ellipses. Smaller uncertainties meant more confident predictions. More confident predictions meant the asteroid's most probable path moved safely away from Earth. The breakthrough came from an unexpected source: archival astronomy images. Don Yeomans and his team realized they could extend Apophis's observational arc by mining databases of astronomical images taken before the asteroid's formal discovery. By finding recovery observations dating back to March 2004, they effectively doubled the time baseline available for orbital calculations. These recovery observations proved decisive. With a longer observational arc and hundreds of additional position measurements, the orbital uncertainty shrank dramatically. By late 2005, refined calculations had reduced the 2029 impact probability to effectively zero. Apophis would indeed make an extremely close approach, closer than any asteroid of comparable size in recorded history, but it would miss Earth by approximately 31,600 kilometers. The final chapter in Apophis's threat assessment required detecting the Yarkovsky effect, the subtle orbital drift caused when an asteroid absorbs sunlight and re-radiates it as heat. This tiny but persistent force can gradually alter asteroid orbits over thousands of years, and accounting for it precisely demands extraordinary measurement precision accumulated over long time periods. That detection came in 2021 when independent teams confirmed that Apophis was drifting away from a purely gravitational orbit at a rate of about 170 meters per year in its semi-major axis. This measured drift was sufficient to rule out passage through the 2036 keyhole and eliminate impact risks for over a century. Today, NASA's analysis confirms Earth is safe from asteroid Apophis for 100+ years, a statement representing one of the most thoroughly validated negative predictions in the history of planetary science. What this means for future threats: the transformation of Apophis from potential civilization ender to confirmed harmless spectacle illustrates science working exactly as intended. Early alarming calculations motivated intensive follow-up observations. Additional data eliminated the apparent threat. The process took several years and involved dozens of observatories worldwide, but it worked. But what if it hadn't worked? What if those additional observations had confirmed rather than eliminated the impact threat? This question haunts planetary defense experts because it illuminates the difference between the threats we've studied and the ones still waiting to be discovered. The interstellar object 3I Atlas teaches us nothing about managing such scenarios. Its hyperbolic trajectory and guaranteed departure from our solar system make it permanently irrelevant to impact risk management. But every lesson learned from Apophis, from initial uncertainty through institutional response to final resolution, provides a template for handling genuine threats that might emerge from ongoing asteroid surveys. As you contemplate these contrasting stories, ask yourself this: which deserves more of our attention and resources? The beautiful alien visitor that poses zero threat, or the systematic work of cataloguing ordinary asteroids that might someday require our intervention? The answer should be obvious, but somehow it isn't. The next section will reveal just how spectacular that 2029 Apophis encounter promises to be, and why it matters far more than any interstellar comet ever could. Section 5, the 2029 show what we'll measure. April 13, 2029 will mark the most intensively observed asteroid encounter in human history. While the 3I Atlas comet disappears forever into interstellar space after its brief visit, Apophis is preparing to deliver something far more valuable than any alien visitor ever could: a front-row seat to witness how asteroids respond to extreme gravitational stress. But here's what will shock you. This isn't just about pretty pictures or breaking news. Footage. The data collected during those crucial hours will reshape everything we know about planetary defense and could someday save our civilization. Every major observatory on Earth will be watching Apophis during its closest approach, armed with instruments that can measure changes in the asteroid's properties down to unprecedented levels of detail. The Global Observation Campaign represents a coordination effort unlike anything attempted for a single astronomical object, and the stakes couldn't be higher for our understanding of cosmic threats. The naked eye spectacle that changes everything picture. This. On the evening of April 13, 2029, millions of people across Europe, Africa, and Western Asia will step outside and look up to witness something unprecedented in recorded history. There, moving visibly across the night sky, will be a 340-meter mountain of rock and metal, close enough to see without telescopes, binoculars, or any special equipment whatsoever. Unlike the 3I Atlas interstellar comet, which requires sophisticated instruments to study from its safe distance of hundreds of millions of kilometers, Apophis will put on a show visible to the naked eye. This isn't just astronomical tourism, it's a natural experiment in celestial mechanics playing out in real time before a global audience. The asteroid will appear as a moving star, traveling fast enough that observers can watch it change position against the background constellations over the course of minutes. Amateur astronomers worldwide have been preparing for this moment for years, coordinating observation campaigns that will contribute meaningful scientific data to professional researchers. But the real excitement happens in the invisible realm of gravitational physics. At its closest approach, just 31,600 kilometers above Earth's surface, Apophis will experience tidal forces roughly 50 times stronger than its own self-gravity. For comparison, the tidal forces Earth experiences from the Moon are about 10 million times weaker relative to our planet's self-gravity. What happens when you stretch and squeeze a 340-meter pile of cosmic rubble with forces that strong? We're about to find out. The gravitational laboratory. Earth's gravitational field will act like invisible hands, stretching Apophis along the line, connecting it to our planet while compressing it perpendicular to that line. These tidal forces don't affect perfectly rigid objects much, but most asteroids aren't solid chunks of rock. They're loose collections of boulders, pebbles, and dust held together by weak gravitational attraction. Think of a bag of gravel rather than a granite boulder. When tidal forces stretch and squeeze such an object, the response depends critically on how tightly the individual components are bound together. If Apophis is relatively coherent, more like fractured bedrock than loose rubble, it might emerge from the encounter relatively unchanged except for its altered orbit and rotation. But if it's a loose aggregate barely held together by gravity, the tidal stress could trigger something extraordinary. Significant surface changes, landslides among loose material, the exposure of fresh subsurface rock that's been protected from solar radiation, and micrometeorite bombardment for millions of years. The timing of maximum tidal stress will occur at precisely 21:46 Universal Time on April 13th, when Apophis passes closest to Earth. At that exact moment, our planet will exert gravitational forces on the asteroid that could literally reshape its surface structure. In real time, ground-based radar systems will play a crucial role in documenting these potential changes. The Goldstone Solar System radar in California and the Green Bank Radio Telescope in West Virginia can achieve meter-level resolution of Apophis during its close approach, potentially revealing details about surface texture, boulder distribution, and any landslides or reshaping triggered by tidal forces. The rotation mystery that could rewrite textbooks. Here's where the 2029 encounter gets really fascinating. Apophis currently rotates once every 30.6 hours, a leisurely tumble that carries different faces into sunlight on a predictable schedule. But Earth's gravity will almost certainly alter this rotation rate, either spinning the asteroid up or slowing it down, depending on complex interactions between tidal forces and the asteroid's elongated shape. Measuring these changes requires extraordinary precision in photometric observations, monitoring how Apophis varies in brightness as different parts of its surface rotate into view. Professional observatories worldwide will contribute data to this effort, but amateur astronomers will also play a crucial role. The International Astronomical Union has been coordinating amateur observation campaigns for years, and the 2029 encounter represents the ultimate test of citizen science capabilities. When was the last time you could contribute to cutting-edge planetary defense research from your own backyard? The thermal infrared observations deserve special attention because they could reveal the most dramatic changes triggered by the encounter. Space weathering, the gradual darkening and reddening of asteroid surfaces caused by micrometeorite bombardment and solar wind exposure, occurs over millions of years under normal circumstances. If tidal stress exposes large amounts of fresh, subsurface material, that material should appear brighter and less red than the space-weathered surface layers. NASA's NEOWISE mission has been conducting thermal infrared surveys of near-Earth asteroids since 2013, providing baseline measurements of surface temperatures and thermal properties for thousands of objects, including Apophis. The 2029 observations will determine whether the encounter altered these thermal characteristics in measurable ways. OSIRIS APEX, the ultimate follow-up. But we won't just be watching from the ground. NASA has repurposed one of its most successful asteroid missions to rendezvous with Apophis after its close encounter with Earth, setting up what promises to be one of the most detailed asteroid studies ever conducted. OSIRIS APEX represents one of the most ambitious repurposing projects in space exploration history. Originally known as OSIRIS-REx, this spacecraft spent 2 years studying the asteroid Bennu, collected samples from its surface in 2020, and successfully delivered those samples to Earth in September 2023. Rather than retire this proven asteroid explorer, NASA extended its mission and retargeted it toward Apophis. The spacecraft will arrive at the asteroid in June 2029, approximately 2 months after its close pass by Earth. This timing is crucial, close enough to the encounter to observe any changes triggered by tidal forces, but far enough removed to allow for safe operations around a potentially altered asteroid. OSIRIS APEX will then spend approximately 18 months conducting the most comprehensive study of a potentially hazardous asteroid ever undertaken by a spacecraft, operating in deep space. The mission's science objectives read like a planetary defense wish list. First priority: document any orbital or rotational changes caused by Earth's gravitational influence. Ground-based observations can measure these changes from afar, but OSIRIS-APEX will provide the precision needed to understand exactly how Earth's gravity modified Apophis's trajectory and spin state. The spacecraft carries instruments originally designed for asteroid characterization that will prove invaluable for post-encounter analysis. The OCAM's imaging system can resolve surface features down to centimeter scales, potentially revealing whether tidal stress triggered landslides, boulder movement, or other surface modifications. Most intriguingly, OSIRIS-APEX will attempt a maneuver that its predecessor never tried at Bennu, a powered descent to within approximately 25 meters of Apophis's surface, followed by a thruster firing designed to disturb and loft surface material. The thruster experiment that could change everything. This sample site reconnaissance won't involve physical contact with the asteroid. OSIRIS-APEX lacks the touch-and-go sampling arm that enabled OSIRIS-REx to collect material from Bennu, but the thruster blast should expose subsurface composition for remote analysis, providing insights that could revolutionize our understanding of asteroid internal structure. The thruster maneuver represents a calculated risk that illustrates how much confidence mission planners have in OSIRIS-APEX's capabilities. Operating at such close range to a potentially modified asteroid requires precise navigation and real-time hazard assessment. If tidal forces did trigger significant surface changes during the Earth flyby, Apophis might present a more hazardous operating environment than originally anticipated. The spacecraft's ability to adapt to changed conditions will be tested immediately upon arrival. OSIRIS-APEX will need to characterize Apophis's post-encounter gravitational field, rotation state, and surface properties before attempting close proximity operations. This represents a unique challenge in spacecraft operations. Most asteroid missions study pristine targets with well-characterized properties, while OSIRIS-APEX will encounter an asteroid that has potentially undergone recent modification. The measurements that matter for planetary defense. From an engineering perspective, the OSIRIS-APEX mission demonstrates remarkable spacecraft longevity and adaptability. By the time it reaches Apophis, the spacecraft will have been operating in deep space for over a decade, far exceeding its original design life. But the real value lies in the data it will collect. By comparing pre-flyby ground-based observations with post-flyby spacecraft data, researchers will gain unprecedented insights into how asteroids respond to strong gravitational perturbations. This information applies directly to planetary defense scenarios where we might need to predict how a threatening asteroid would behave if deflected by a kinetic impactor or gravitational tractor. The mission will also validate computational models used to simulate asteroid deflection missions. Current models make assumptions about asteroid internal structure, surface properties, and mechanical response to external forces. OSIRIS-APEX observations of Apophis's actual behavior during and after its Earth encounter will provide ground truth for these simulations. Data collection will focus on several key parameters that matter for planetary defense applications. Surface roughness and boulder distribution affect how momentum transfer occurs during kinetic impact missions. Internal structure and mechanical properties determine how an asteroid responds to deflection attempts. Composition and thermal properties influence the effectiveness of various deflection techniques. The coordination between ground-based and space-based observations during the Apophis encounter will set new standards for international scientific cooperation. Radar facilities, optical telescopes, and space-based infrared observatories will work in concert with OSIRIS-APEX to create the most comprehensive data set ever assembled for a single asteroid. The global coordination that puts 3i Atlas to shame while. The interstellar comet 3I Atlas generated scientific interest for its exotic origins. The practical coordination around its observations pales in comparison to what's being planned for Apophis. The 2029 encounter will demonstrate the kind of international cooperation that makes planetary defense possible. The European Space Agency's Hera mission, launched in October 2024, will be operating in the vicinity of the Didymos asteroid system during Apophis's encounter with Earth. While Hera won't observe Apophis directly, its advanced instruments and operational experience with asteroid characterization will inform data analysis and interpretation for the encounter observations. The mission timeline reflects careful planning around astronomical constraints and operational considerations. OSIRIS-APEX's arrival in June 2029 allows enough time for Apophis to move away from Earth's gravitational influence while remaining close enough to our planet for efficient communication and data relay. The 18-month operational phase provides multiple opportunities to observe Apophis under different lighting conditions and orientations. This extended timeline ensures comprehensive coverage of the asteroid's modified properties, something impossible with brief flyby missions or limited ground-based observation windows. Perhaps most importantly, OSIRIS-APEX will demonstrate that asteroid characterization missions can be extended and repurposed to address planetary defense questions. The spacecraft's original mission to Bennu focused primarily on understanding asteroid composition and formation processes. Its extended mission to Apophis explicitly targets planetary defense applications, showing how basic science and applied research complement each other in asteroid exploration. As we prepare for this unprecedented encounter, ask yourself, when has any interstellar object offered such practical, actionable insights for protecting our planet? The answer reveals everything about where our priorities should lie when it comes to cosmic threats. The next section will explore the current state of planetary defense and how the lessons from Apophis are already reshaping our approach to cosmic threats. Section 6, the OSIRIS-APEX mission, humanity's greatest space detective story. Sometimes the universe provides perfect timing that makes you question whether we're living in a carefully orchestrated cosmic drama. As 3I Atlas fades into interstellar obscurity and Apophis prepares for its historic 2029 Earth flyby, NASA has positioned one of its most capable spacecraft to witness the aftermath firsthand. This isn't just another space mission, it's humanity's first chance to study an asteroid that's been fundamentally transformed by Earth's gravitational embrace. But here's what will shock you about this $800 million detective story unfolding. In deep space, the spacecraft tasked with solving this cosmic mystery wasn't even originally designed for this mission. The ultimate mission. Makeover meet OSIRIS-APEX, formerly known as OSIRIS-REx, a spacecraft that has already made history by successfully collecting samples from asteroid Bennu and delivering them to Earth in September 2023. Rather than retire this proven asteroid explorer, NASA made a decision that represents one of the most audacious repurposing projects in space exploration history. The transformation from OSIRIS-REx to OSIRIS-APEX, origins, spectral interpretation, resource identification, security Apophis Explorer, represents everything brilliant about modern space exploration. Instead of building an entirely new spacecraft at enormous cost, engineers recognized that their existing asteroid specialist could be retargeted toward Apophis, creating an unprecedented opportunity to study the 2029 encounter's aftermath in the exquisite detail. Think about the timing here. OSIRIS-APEX will arrive at Apophis in June 2029, approximately 2 months after the asteroid's closest approach to Earth. This window is crucial, close enough to the gravitational encounter to observe any changes triggered by tidal forces, yet far enough removed to allow for safe operations around a potentially altered asteroid. The James Webb Space Telescope will document the flyby from afar, but OSIRIS-APEX will get up close and personal with whatever emerges from Earth's gravitational gauntlet. For 18 months, this robotic detective will conduct the most detailed study of an asteroid ever undertaken by a spacecraft operating in deep space. The science wish list that keeps researchers awake here's where this mission transforms from impressive engineering feat to potentially revolutionary scientific endeavor. OSIRIS-APEX's science objectives read like a planetary defense researcher's dream scenario, a comprehensive investigation of how a potentially hazardous asteroid responds to the kind of gravitational stress it might experience during deflection attempts. First priority: document any orbital or rotational changes caused by Earth's gravitational influence. While ground-based observations can measure these changes from millions of kilometers away, OSIRIS-APEX will provide the precision needed to understand exactly how Earth's gravity modified Apophis's trajectory and spin state down to centimeter level accuracy. The spacecraft carries a suite of instruments originally designed for asteroid characterization that will prove invaluable for post-encounter analysis. The OCAM's imaging system can resolve surface features down to centimeter scales, potentially revealing whether tidal stress triggered landslides, boulder movement, or other surface modifications during the close approach. But wait, there's something even more intriguing about what this mission might discover. The OTS thermal emission spectrometer will map temperature variations across Apophis's surface, searching for thermal signatures that might indicate freshly exposed subsurface material. If Earth's tidal forces did strip away space-weathered surface layers, revealing pristine rock beneath, OSIRIS-APEX should detect the temperature differences between old and new surfaces. Most audaciously, the spacecraft will attempt a maneuver that its predecessor never tried at Bennu, a powered descent to within approximately 25 meters of Apophis's surface, followed by a thruster firing designed to disturb and loft surface material. This isn't sample collection. OSIRIS-APEX lacks the touch-and-go sampling arm that enabled OSIRIS-REx to collect material from Bennu, but the thruster blast should expose subsurface composition for remote analysis. The calculated risk that could rewrite textbooks. The thruster maneuver represents a calculated gamble that illustrates just how much confidence mission planners have in OSIRIS-APEX's capabilities. Operating at such close range to a potentially modified asteroid requires precision navigation and real-time hazard assessment capabilities that push the boundaries of autonomous spacecraft operation. Consider the challenge. If tidal forces did trigger significant surface changes during the Earth flyby, landslides, boulder redistributions, changes in surface texture, Apophis might present a more hazardous operating environment than originally anticipated. The spacecraft's ability to adapt to altered conditions will be tested immediately upon arrival. OSIRIS-APEX will need to characterize Apophis's post-encounter gravitational field, rotation state, and surface properties before attempting close proximity operations. This represents a unique challenge in spacecraft operations. Most asteroid missions study pristine targets with well-characterized properties, while OSIRIS-APEX will encounter an asteroid that has potentially undergone recent modification by forces we've never observed in action. Navigation around Apophis will require extraordinary precision under any circumstances. The asteroid's elongated shape and relatively rapid rotation create a complex gravitational environment that changes as different parts of the asteroid face the spacecraft. If Earth's tidal forces altered the rotation rate or axis orientation, mission planners will need to update their operational procedures in real time based on OSIRIS-APEX's initial observations. The scientific payoff could be enormous, or it could fundamentally challenge our understanding of asteroid mechanics. By comparing pre-flyby ground-based observations with post-flyby spacecraft data, researchers will gain unprecedented insights into how asteroids respond to strong gravitational perturbations. The Planetary Defense Connection. Here's why this mission matters for everyone living on the third rock from the Sun. OSIRIS APEX will validate computational models used to simulate asteroid deflection missions. Current models make assumptions about asteroid internal structure, surface properties, and mechanical response to external forces that have never been tested under controlled conditions. The 2029 Earth encounter represents a natural experiment in asteroid mechanics that we could never replicate artificially. Earth's gravitational field will stretch and compress Apophis with forces roughly 50 times stronger than the asteroid's own self-gravity, similar to the stress levels that might be generated during kinetic impactor deflection attempts. If OSIRIS APEX discovers that Apophis responded differently to tidal stress than our models predicted, whether more dramatically or less so, those findings could revolutionize how we design future planetary defense missions. The data collected during this mission will influence deflection mission planning for decades to come. The timing couldn't be more perfect for validating these models. NASA's DART mission successfully demonstrated kinetic impactor technology by crashing into the asteroid Dimorphos in 2022, proving that we can change an asteroid's orbit when we hit it hard enough. OSIRIS APEX will provide the detailed follow-up data needed to understand exactly how that momentum transfer process works in different scenarios. The European Space Agency's Hera mission, which will arrive at the Didymos system in late 2026 to study DART's impact aftermath, will provide additional validation data for our deflection models. Together, DART, Hera, and OSIRIS APEX represent humanity's first comprehensive investigation of asteroid deflection physics. The engineering marvel hiding in plain sight. From an engineering perspective, the OSIRIS APEX mission demonstrates remarkable spacecraft longevity and adaptability that should give us confidence in humanity's growing space exploration capabilities. By the time it reaches Apophis, the spacecraft will have been operating in deep space for over a decade, far exceeding its original design life. The successful extension of OSIRIS-REx into OSIRIS APEX provides a template for future missions that could potentially visit multiple targets during extended operational phases. This approach maximizes the return on investment for expensive deep space missions while building institutional knowledge about long-duration spacecraft operations. But there's something even more impressive about this mission's technical challenges. Coordination between ground-based and space-based observations during the Apophis encounter will set new standards for international scientific cooperation. Radar facilities, optical telescopes, space-based infrared observatories, and OSIRIS APEX will work in concert to create the most comprehensive data set ever assembled for a single asteroid. The mission timeline reflects careful planning around astronomical constraints and operational considerations. OSIRIS APEX's arrival in June 2029 allows enough time for Apophis to move away from Earth's gravitational influence while remaining close enough to our planet for efficient communication and data relay. The 18-month operational phase provides multiple opportunities to observe Apophis under different lighting conditions and orientations, building up a complete picture of how the asteroid changed during its Earth encounter. The questions that keep scientists guessing. Data collection will focus on several key parameters that matter for both basic asteroid science and planetary defense applications. Surface roughness and boulder distribution affect how momentum transfer occurs during kinetic impact missions. Internal structure and mechanical properties determine how an asteroid responds to deflection attempts. Composition and thermal properties influence the effectiveness of various deflection techniques. The thruster disturbance experiment deserves special attention as a proof of concept for future planetary defense missions. By documenting how Apophis's surface material responds to artificial disturbance, OSIRIS-APEX will provide insights into regolith properties that could inform the design of more aggressive deflection techniques. If surface material proves loosely bound and easily disturbed, that knowledge could influence decisions about kinetic impactor design or alternative deflection methods. If it proves more cohesive than expected, deflection missions might need to deliver more energy to achieve desired trajectory changes. The mission will also serve as a pathfinder for future asteroid rendezvous operations in an era of expanded planetary defense activities. As near-Earth asteroid surveys identify more potential threats, space agencies may need to dispatch characterization missions on relatively short notice. OSIRIS-APEX's operational experience at Apophis will inform the design and procedures for such rapid response missions. The public engagement opportunity, unlike most deep space missions that study distant or obscure targets, Apophis will be familiar to the public through its 2029 Earth flyby. The spacecraft's detailed follow-up study provides a natural continuation of the story, maintaining public interest in asteroid science and planetary defense beyond the initial flyby excitement. The mission's data will likely influence asteroid risk assessment methodologies for decades to come. Current impact hazard calculations rely on statistical models of asteroid properties derived from limited observational data. OSIRIS-APEX will provide the kind of detailed ground truth measurements needed to validate and refine these models, potentially improving our ability to assess threats from newly discovered asteroids. Think about the educational potential here. Students will be able to follow a complete asteroid story from initial discovery and threat assessment through detailed scientific characterization. The Apophis narrative provides an ideal framework for teaching orbital mechanics, risk assessment, scientific methodology, and international cooperation in space exploration. The mission represents humanity's growing capability to transform apparent threats into opportunities for scientific advancement. The same asteroid that once appeared to threaten civilization is now serving as a natural laboratory for understanding planetary defense challenges. The legacy that extends beyond Apophis as OSIRIS-APEX prepares for its extended mission to Apophis. We're witnessing the maturation of planetary defense from reactive crisis management to proactive scientific investigation. The spacecraft that successfully sampled one asteroid will now study another that has been fundamentally altered by gravitational forces we're only beginning to understand. The data collected during this mission will influence how we think about asteroid deflection for the rest of the 21st century. Every measurement OSIRIS-APEX makes, every surface change it documents, every model it validates or challenges will contribute to our growing ability to protect Earth from future cosmic threats. But perhaps the most important legacy of this mission will be demonstrating that with sufficient planning, international cooperation, and technological capability, apparent existential threats can be transformed into unprecedented scientific opportunities. The question now isn't whether OSIRIS-APEX will make important discoveries about Apophis, it's whether those discoveries will fundamentally change how we prepare for the next potentially threatening asteroid that surveys will inevitably find lurking in the depths of space. Are you ready to follow along as this cosmic detective story unfolds? Because the greatest space investigation in human history is about to begin, and the evidence it uncovers might just determine our species' long-term survival. Chapter 7. Risk Communication and Public Understanding. The most dangerous moment in planetary defense isn't when a comet like 3I Atlas captures headlines. It's when the public stops paying attention to the threats that actually matter. While the interstellar comet generates thousands of articles and social media posts about its alien origins, the systematic work of cataloging potentially hazardous asteroids continues in relative obscurity. This communication gap represents a fundamental challenge that could determine humanity's preparedness for genuine cosmic threats. Consider the stark contrast in coverage between 3i Atlas and the hundreds of near-Earth asteroids discovered each year. The interstellar comet, despite posing zero threat to our planet, dominates astronomy news feeds with breathless updates about its exotic composition and mysterious journey through space. Meanwhile, asteroid 2024 PT5, which passed within the lunar distance just last month, barely registered a mention in mainstream media. Yet which object actually matters for planetary defense? The James Webb Space Telescope's observations of 3i Atlas provide a perfect case study in misallocated scientific attention. While Webb's unprecedented infrared capabilities reveal fascinating details about the comet's chemical composition, potentially offering insights into star formation in distant stellar systems, these discoveries contribute nothing to our understanding of impact risks or deflection techniques. The same observational time could be spent characterizing newly discovered potentially hazardous asteroids, building the knowledge base needed to protect Earth from genuine threats. But here's where the psychology of risk communication becomes truly problematic. Human brains are evolutionarily wired to respond to novel, unusual stimuli while ignoring familiar, routine patterns. 3i Atlas triggers every cognitive bias that makes objects seem threatening. It's rare, mysterious, and arrives from alien territory. The fact that it poses no actual danger gets buried beneath layers of sensationalized coverage about visitors from another star. This cognitive mismatch between perceived and actual risk extends far beyond astronomy. We see the same pattern in public responses to airline safety, nuclear power, and infectious disease outbreaks. The dramatic but statistically insignificant events capture attention and resources, while the mundane but genuinely dangerous threats accumulate unnoticed in the background. The communication challenge becomes even more complex when we consider the institutional incentives driving science journalism. Editors and producers know that alien comet approaches solar system generates far more clicks and engagement than routine asteroid survey discovers 47 new near-Earth objects. The economic realities of modern media systematically favor spectacular but irrelevant stories over important but unglamorous developments. Space agencies have learned these lessons the hard way through previous encounters with interstellar objects. When Oumuamua was discovered in 2017, the initial scientific uncertainty about its composition and trajectory generated wild speculation about artificial origin and potential threats. The subsequent discovery of 2I Borisov in 2019 was handled more carefully, with clear communication about its harmless nature and scientific significance. NASA's approach to 3i Atlas represents the current best practices in interstellar object communication. Every official statement begins with explicit confirmation that the comet poses no threat to Earth, followed by technical details about its trajectory and scientific value. This represents a deliberate reversal from earlier communication strategies that buried safety assessments in technical jargon while leading with proximity statistics. The European Space Agency has adopted similar protocols, consistently emphasizing safety before scientific details. But even these improved communication strategies struggle against the fundamental appeal of alien visitor narratives. Social media algorithms amplify sensational content, creating echo chambers where spectacular but false interpretations spread faster than accurate but mundane scientific facts. Here's what every space enthusiast needs to understand. The next genuinely threatening asteroid won't announce itself with exotic origins or mysterious compositions. It will be discovered by routine survey programs catalogued with mundane alphanumeric designations and characterized through patient observation campaigns that rarely make headlines. The asteroid that keeps planetary defense experts awake at night has a name like 2025 RX-12, not something exotic like 3i Atlas. The upcoming 2029 encounter with Apophis offers an unprecedented opportunity to demonstrate effective risk communication. Unlike 3i Atlas, which will disappear forever into interstellar space, Apophis represents a genuine member of the potentially hazardous asteroid population. Its close approach, threading between Earth and our geostationary satellites, will be visible to the naked eye across much of the world. The communication challenge for Apophis mirrors but inverts the 3i Atlas problem. How do you explain that? An asteroid passing closer than our satellites is completely safe, while maintaining public trust in scientific risk assessment? The key lies in the same mathematical precision that eliminated Apophis as a threat. Orbital mechanics leaves no room for interpretation when calculations are based on sufficient observational data. Educational institutions worldwide are developing curriculum materials around the Apophis encounter that emphasize both the spectacular nature of the event and the systematic scientific process that confirmed its safety. These materials offer teachers a perfect opportunity to illustrate the difference between proximity and danger, uncertainty and risk, spectacular and significant. Amateur astronomy communities are already planning coordinated observation campaigns for both 3i Atlas and the 2029 Apophis encounter. These grassroots efforts provide valuable opportunities for public engagement while contributing meaningful scientific data. The International Astronomical Union has been working with amateur organizations to develop standardized observation protocols that could serve as models for future encounters. But the most important audience for improved risk communication may be policymakers who control funding for planetary defense programs. The exotic appeal of interstellar objects like 3i Atlas can actually help justify continued investment in asteroid surveys and characterization efforts, if the message is framed correctly. The same public fascination that drives media coverage of harmless comets can be redirected toward genuine planetary defense priorities. The upcoming NEO Surveyor mission, scheduled for launch no earlier than late 2027, represents exactly the kind of systematic capability building that needs sustained public and political support. This space-based infrared telescope will discover thousands of previously unknown potentially hazardous asteroids, filling critical gaps in our knowledge of the threat population. Unlike missions designed to study specific exotic objects, NEO Surveyor's success will be measured by the comprehensiveness of its catalogue. Think about it this way: every dollar spent studying 3i Atlas is a dollar that could be invested in NEO Surveyor or similar systematic survey programs. Every hour of telescope time devoted to interstellar visitors is an hour not spent tracking potentially hazardous asteroids that might pose future threats. The opportunity cost of misallocated attention extends beyond public engagement to real resource allocation decisions. The Vera C. Rubin Observatory, beginning operations in 2025, exemplifies the unglamorous but essential work of planetary defense. The legacy survey of space and time will discover more asteroids in its first year than all previous surveys combined, providing the comprehensive catalogue needed for effective threat assessment. Yet LSST generates minimal public excitement compared to exotic visitors like 3i Atlas. International cooperation frameworks like the International Asteroid Warning Network and Space Mission Planning Advisory Group focus on the mundane but critical coordination tasks that make planetary defense possible. Standardizing observation procedures, sharing data across borders, developing response protocols for confirmed threats. These organizations don't generate headlines, but they provide the institutional foundation for protecting Earth from cosmic impacts. The success of risk communication ultimately depends on building scientific literacy that extends beyond individual encounters to systematic understanding of how planetary defense actually works. The goal isn't just explaining why 3i Atlas is harmless, but helping the public understand how we assess and respond to space hazards in general. As 3i Atlas continues its journey through our solar system and Apophis prepares for its historic encounter with Earth, we face a fundamental choice about how to frame these events for public consumption. We can continue chasing exotic curiosities that pose no threat, or we can use these high-profile encounters as opportunities to educate the public about genuine hazards and the systematic efforts to address them. The universe doesn't care about our preference for spectacular over significant. Asteroids follow the laws of physics, not the laws of journalism. Our survival depends on aligning public attention with actual risks, not just the ones that generate the most compelling headlines. The real test of planetary defense communication isn't how well we explain individual objects, but how effectively we build lasting public support for the systematic capabilities that protect our planet from threats we haven't yet discovered. Chapter 8. The Real Enemy: Complacency and Future Preparedness. The greatest threat to humanity's survival in the cosmic shooting gallery isn't a specific asteroid, it's the complacency that pretty visitors like 3i Atlas can breed about the mundane threats that actually matter. While we marvel at the interstellar comet's exotic journey through our solar system, statistical inevitability continues its patient work, gradually aligning orbital mechanics and probability theory in ways that could spell disaster for our civilization. Consider this sobering reality. Somewhere out there, following an elliptical orbit we haven't yet characterized, there's likely an asteroid with Earth's name on it. Not because of any cosmic malevolence, but because mathematics doesn't care about our preferences or preparations. The same gravitational forces that safely guide 3i Atlas past our planet at 268 million kilometers also govern the trajectories of thousands of potentially hazardous asteroids that pass much, much closer to home. The success story of Apophis demonstrates both our growing capabilities and our persistent vulnerabilities. The transformation of this asteroid from civilization-ending threat to confirmed harmless encounter required 2 decades of sustained observation, international cooperation, and technological advancement. But what happens when the next Apophis-class object is discovered and the initial orbital calculations don't improve with additional data? The DART mission's successful deflection of Dimorphos proved that kinetic impact technology works under controlled conditions with years of advanced planning. But the smaller asteroids that make up the majority of undiscovered near-Earth objects might not provide such generous warning times. A 100-meter asteroid could potentially arrive with only months of advance notice, requiring rapid response capabilities that don't currently exist. Here's what keeps planetary defense experts awake at night. The Torino scale, our primary tool for assessing asteroid impact threats, has never recorded a confirmed level 10 event, certain collision with global catastrophe. But mathematical probability suggests that such events are inevitable given sufficient time. The question isn't whether a genuinely threatening asteroid will be discovered, but when and whether our current capabilities will prove adequate for the challenge. The upcoming NEO Surveyor mission represents humanity's most ambitious attempt to catalogue the remaining threat population. This space-based infrared telescope will detect dark asteroids invisible to ground-based optical surveys, potentially revealing hundreds of previously unknown potentially hazardous asteroids in the city-killer size range. But discovery is only the first step. Each new object requires years of follow-up observations to determine its orbit precisely enough for confident risk assessment. The Vera C. Rubin Observatory will contribute unprecedented sky coverage and sensitivity when it begins operations in 2025. The Legacy Survey of Space and Time could discover more asteroids in its first year than all previous surveys combined. Yet even these advanced capabilities cannot eliminate the fundamental challenge of orbital uncertainty that made Apophis appear threatening during its early observational arc. Think about the institutional memory problem facing planetary defense programs. The scientists and engineers who lived through the Apophis scare of 2004-2006 are approaching retirement. The next generation of researchers will inherit sophisticated tools and protocols, but may lack the visceral understanding of how quickly apparent threats can escalate from scientific curiosity to public crisis to policy emergency. The communication, lessons learned from 3i Atlas and Apophis must be preserved and refined as we face future discoveries. The exotic visitor captures attention through mystery and rarity, while the genuine threat accumulates quietly in routine survey data. Training the next generation of science communicators to redirect public fascination from spectacular but harmless objects towards systematic planetary defense capabilities represents a critical challenge.